All right, so I typed the two equations in. I'm going to turn off the second equation, so just enter on the equal sign. And just a zoom 6, just see what's going on there. Now, it's one of those things where I have the experience, and now you kind of do too from the last example that we did. This one is asymptotic with the x-axis. It just, I mean, you take a look at it at first glance, there's always that little bit of doubt where it's like, is it really asymptotic? I don't know. Is there an asymptote there? Well, if that is the case, if there's an asymptote there, what that's telling me is that no matter how far I go out to the left, it's never going to hit the x-axis. So it's never going to hit 0, all right? So it may approach 0, but it's never actually going to get there. And so if that's the case, for each additional step we take toward the left, we're going to accumulate more and more area. All right? Infinity is this, I mean, it's got such a bad rap. It kind of has been explained as a destination, which I think is unfair. Right? Infinity is not a destination, especially when you're talking about like a limit. It says the limit as x approaches infinity. Infinity is a moving target, so you take a step towards infinity, infinity takes a step away from you. All right, so you can never get there because it's always one step ahead of you. All right, so when I say I'm approaching infinity, the best I can do is aim for infinity. Like I'm never going to get close, and even if I got close, infinity would just move away. All right, so it's not a static object. It's not finite. It's by definition not finite. So when I'm trying to capture an area, and it's asymptotic with, like, let's say the x-axis, if it never gets to the x-axis, then I can never capture the true area. Now I could come up with an approximation of what that area might be, but I'll never actually be able to capture the true area. All right, so that's the first graph. And you know, after we did the first example, you take a look at this one and you say, okay, I can kind of see it maybe. Just remember that this one's going to the left because it's a is approaching negative infinity, or a is approaching infinity, but it's negative a within the integral. Bottom line is we're going to the left, not to the right in this case. All right, so that's the one thing. Now the other graph is the graph of the antiderivative function. So I'm going to hit enter on the equal sign and turn off my first equation, and then hit enter on the equal sign to turn on my second one. Normally I wouldn't bother with that, I just graph them simultaneously, but the issue is the way we did this problem, we want a going to infinity. So for the antiderivative function, so I need this to go to the right. So I'd have an issue with zoom stuff. So I'm going to hit zoom 6 again, and we see what this graph looks like. All right, it's cool, it's a graph. But what we're going to do with this graph is a little bit different. All right, here we're trying to find the y value that we're getting closer and closer to as x goes out to infinity. All right, so we're not looking at area anymore. Right, that's a big difference. So the way you handle, and you may have experienced this in Calc 1, depending on your teacher, the way you handle limits as you go out to infinity, in your table set, so second window, table start at 0, that's fine, but make your change in table something large. Doesn't have to be too large, make it like 100. The idea is that, yeah, I can't actually go out to infinity on these calculators, but I can get really large really fast if I want to. All right, so second graph, now I'm in the table and I'm increasing by 100s. All right, now as I'm increasing, the x value, if it's going to converge, it should actually do just that. It should be zeroing in on a particular number. All right. So you might see like a dramatic change. If it's going to converge, you might see a dramatic change early on, but as the x values get larger and larger, you'll see a smaller and smaller change. So like, for example, at the bottom of the screen, we have 59.372. If this was going to converge, let's say on 60, the next one would be like 59.572, maybe 59.972, and so on. And then as you increase, you'll see that it's closing in particularly on 60, but this doesn't seem to be closing in on anything. In fact, the x values seem to be getting larger and larger without any indication that it'll be slowing down anytime soon. All right, if you're in doubt, make your change in table something even bigger. Maybe go to the 10,000s. It's still increasing. There's no indication that it's slowing down its rate of increase. All right, maybe try 100,000. Eventually the calculator has enough, and it's like, please stop. But we're not there yet. 100,000, it's still increasing. All right, there's no reason for me to think that this is settling down. Now, is this enough for you to say that it's divergent without doing any of the other work that we did? I don't know, maybe. Like the safe bet is to do all the other work and use this to confirm your answer. All right, but in a pinch, at least you have something, right? So let me just show you really quickly what would happen if your function were actually going to converge on a particular value. So I'll just make up something on the fly here. Let's say we have 3x squared over 5x squared minus 5x plus 2. I don't know, something. All right, so I'll change my settings back to what they were, and I'll go to the zoom 6. I have a graph. If I'm going out to infinity, or even negative infinity, just based off the picture, it's a pretty safe assumption that it's going to level off somewhere. It's just a question of where. All right, so I go into my table set, 0, make it something big, like start with 100. And you can see that it seems to be leveling off at a particular number. Pretty safe assumption that it's 0.6, but maybe you're in doubt. So increase it, just go right for it. Increase it to 10,000. Yeah, it's 0.6. All right, it's 0.6 something, but even the calculator's given up coming up with estimates. It's like, please, just like, if you haven't figured it out by now, I'll just scream it at you. It's 0.6. All right, so you can get your limit as x approaches infinity using the calculator. The only time that it could be troublesome is if you have discontinuities. All right, you might have to work around those, but you know, this is one of those strategies where, I don't know, when I was in Calc 1, I didn't know this strategy. So I learned all that horizontal asymptote rules and every rule that you could think of. And then I became a teacher and I learned this strategy, and I was like, that would have been nice to know in Calc 1. Would have got all those limit questions right, except the ones that tell you to do it by hand. But at least you know going in what the correct answer is supposed to be. The one recommendation I give you is that if you're using this technique for anything, and this unit is limit heavy, right? Limits all over the place. All right, so if limits were not one of your strengths, and in fact, it's one of those, you know, back in Calc 1, you're like, why the hell are we doing so much with limits? This is outrageous. We don't need limits. We don't need so much with limits in order to understand a derivative. You didn't need to know it to understand a derivative. You needed it to have the foundation to understand what we're going to do in this unit. All right, so if you're weak on limits, these calculator strategies are going to save your life. All right, and I really don't think I'm exaggerating when I say that.